In this topic, we're going to look at capacitance. Now, what is capacitance? Now, a capacitor is like a charge bucket. Here's a bucket. So, we have a large bucket here, so it's basically going to be a big capacitance. It's able to store lots of charge. So the bigger the bucket, the more charge it can store. And this is the symbol for it. Now, the charge that we can put in this bucket depends on two things, effectively. The first is the capacitance. It's the size of the bucket, the amount of space that's inside it, let's say. And this is measured in farads. The second thing is the potential difference. So in other words, if we have a large potential difference, we can push and squeeze more charge into that bucket. And this is measured in volts. So it depends on the capacitance, its capacity, and the potential difference. If we have a large potential difference, we can squeeze, push more charge into the bucket. And this is the equation. The charge that we're able to put in this capacitor depends on the product of the potential difference times by the capacitance of this bucket. So we're going to look a little bit more about what a capacitor is. This is a symbol. We have one blue plate and one orange plate. So we have two parallel conducting plates, each of area A, and the distance between them is D. Notice they don't touch, there's a space between them. Now, if you put positive charge on the top plate and negative charge on the bottom plate, these opposite charges will attract each other. So it means that you can actually put even more charge because there's this ability to store more charge because they're attracted to the charge on the other plate. So there's the charge. Now, the capacitance of these two plates depends on the design of the capacitor. It depends on the area, A, of the plates. It depends on D, the distance between the plates. And it also depends on the medium or the material between the plates. We have this thing called the dielectric property, which is epsilon, which is the thing that goes between the plates. And this is the equation we use. So the capacitance depends on the dielectric property. It depends on A, which is the area between the area of the plates, and the distance between the plates. So the capacitance of this capacitor can be increased by designing the capacitor in such a way that we can 1. Increase the area, or 2. Decrease the distance between the plates, or 3. Use a medium with a higher dielectric property, in other words a higher permittivity of free space. The lowest value for the permittivity is for a vacuum or for air. If we put another medium between them, we can increase this value. And here we have the permittivity of free space, epsilon naught, which is for free space or for a vacuum, is basically 8.85 times 10 to the minus 12 coulombs squared per Newton per meter squared. And here we have a set of values which compare the material with that of air or vacuum. For example, vacuum, of course, is 1, so it's the same material. Air is basically the same. If you put paper between the plates, you can get a capacitance which is going to be 4 times as great. Polystyrene will be 3 times as great. A ceramic material could be between 100 and 15,000 times as great. So, by using different materials, you can increase this dielectric property. In other words, increase the capacitance. And here we have another table. Metals have a really high, which means they have a really high permittivity of free space, basically, because they can conduct. And this gives this the material the the ability to, let's say, transmit an electric field. So water is 80 or 90, and so on. So let's look at what commercial capacitors look like, bearing in mind this equation. So this is basically what it is. Two plates with a dielectric material between them. This is one way of making it, by having long sheets that roll up, and that way that's why many capacitors are cylindrical shaped, like this one here. Here we have a variable capacitor. We have a rotor which is able to move in and out, and the stator is basically fixed. So the rotor is moved around, so it makes the metal plates move, these upper plates move in between the plates in the stator. So if we're able to move these plates so that we increase the overlap, what do you think would happen to the capacitance? Basically, by moving the plates between the others, this effectively increases the area of overlap, A, and this would increase the capacitance. So you can basically manipulate the capacitance of this by turning this this knob, and then this would increase the overlap here. So by increasing the area, we increase the capacitance. Let's look at basically what a capacitor does. We have a capacitor here on the left, and we have a battery on the right, but at the moment they're not connected, so we will connect them. 1, 2. Now they're connected. Now the charge is free to move from the battery onto the capacitor plates, so that's what it does. So there's a free moving current onto the plates. So we connect the capacitor to a potential difference of 20 volts. The cell starts to push charge around the circuit onto the plates. Since the plates are quite close, they're attracted to the charge on the facing plate, as we discussed before. So with time, more and more charge will land onto the plates. Now eventually, after the charge starts to fill the plates, this charge will resist the arrival of more charge, so it becomes harder and harder to charge the plates. Eventually the plates get so full of charge that they basically repel all further charge and stop any further charge from arriving. At that point, the potential difference across the plate will be equal to the potential difference across the battery. So then, therefore, it's basically fully charged, or you could say the capacitor is fully charged. So this is basically what a capacitor is. It's an ability, it's a bucket which is able to store charge, which depends on the voltage and depends on the capacitance. The capacitance depends on the area of overlap, it depends on the distance between the plates, and it depends on the dielectric property of the material between the plates.